Tertiary structure. What do we got for tertiary structure? Okay. What the hell is that?
It's in the sky.
I don't know if I can fix that. Okay. And I heard side chain. Okay. So tertiary protein has no function until it forms a tertiary structure, and that tertiary structure is formed by the side chain interactions. How about the quaternary structure?
Two or more separate peptide chains that come together and make a big protein.
This also is protein structure. Protein function. So your protein has function if it has a tertiary structure. Unless that tertiary structure is supposed to be connected to another tertiary structure, then it doesn't have function until it becomes that quaternary structure. We okay with that? If I'm a protein and I need two quaternary structures, the individual quaternary structures can't function. They only function when the two tertiary structures come together to make the quaternary structure. The best example is hemoglobin. There are 4 tertiary structures, 2 pairs of identical tertiary structures. None of those 4 can carry oxygen, but when they come together as 4, they form a tertiary structure that can carry oxygen. But most proteins do not need a tertiary structure. Every protein needs a primary, secondary, and tertiary, and only a few need quaternary. So that quaternary is only if you need to go one step further to give it function. And these would be really large proteins. All right. So contrasting comparative, competitive and non-competitive, and use this plot to help with the discussion. So what do we want to say about this? How about the competitive?
It attaches to the active site, but increasing the substrate. Yeah, what was that? Good word, thank you.
So the competitive inhibitor fights for the active site on the protein. And you can overcome this by flooding the substrate, flooding the solution with substrate. So every time that the enzyme finishes a reaction, it looks to see what it can react on next, and if all it really sees is substrate, then it just goes after that substrate. So if there's one inhibitor and there's 100 substrates, the chances of it getting the inhibitor instead of the substrates is less than 1%. So that's how you handle that situation. Just flood it with substrate. But how about the non-competitive? it just T? Yeah, it is just T. So since the non-competitive inhibitor attaches to someplace other than the active site, you can't just throw a whole bunch of substrate in and fight it. It's actually deactivating the substrate by messing with the backside, deactivating the enzyme by messing with the backside of the enzyme. So now the enzyme's active site isn't correct. So an enzyme is what? What kind of substance? It's a protein. So in that tertiary structure, if you modify the tertiary structure, what happens to the protein's function?
Stops.
It stops or it slows down. So if you attach something to another part of the protein, that protein itself's tertiary structure, its folding, will be kinked or warped or morphed into a way that it won't fit whatever's supposed to be fitting into it anymore. And so when you have a non-competitive inhibitor working on an enzyme, you're kind of in trouble because you can't do anything to stop it. You would have to have another substance entered into the body that would actually grab the inhibitor and pull it off of the enzyme. So that would be, an antidote of some sort. So if it's some sort of like heavy metal poisoning, then you'd put a chelating agent which would go in and find heavy metals and pull them off. And you could make it after that. So in this graph, you see that if you just keep jacking up the substrate concentration, you can overcome the competitive inhibitor, but it doesn't matter how much substrate you put in. I could put tons of substrate in down here, and I've still got my non-competitive slowing down my maximum turnover rate of my enzyme. All right, so I toss some trypsin into this insulin solution, and what happens? What does trypsin do? So trypsin is an enzyme which selectively cleaves a substrate peptide bond following a basic amino acids, arginine and lysine. So anytime I've got an arginine and anytime I've got a lysine, I'm going to get this piece of protein cut. So we go back to the notes here. A and K? A and K? Is that right? R and K?
Yeah.
Okay. All right. So every time I've got, it's not A because A is alanine. So
do they have to be like
The very first one.
KRK?
oh, I missed the very first one. No, it doesn't.
So it can be, okay, because that's where I was kind of confused as to.
As soon as it sees a K or an R,
Okay.
a lysine or an arginine, then it cleaves right after the molecule,
Okay.
right after that amino acid. So then you just cruise along here, and here's an R, so it's going to cut it there, and
Okay.
it'll cut it there, and there,
Okay,
and there.
that's what I wrote first, but I erased it all.
There's K and an R
Oh, there's an R.
Okay.
and a K.
Oh, there's a K. It's amazing how easy that is to miss. Did I miss another one? Is that it? So the protein isn't completely broken down into individual amino acids. There are several polypeptides, but is this thing going to work anymore? Certainly not, absolutely not. The primary structure has been broken. So if I wanted to break it down further, what would I do?
And
Add another enzyme that would cut it up into more places? Sure. Okay, so what's happening in this first diagram here?
The substrate concentration's going up and the reaction's going up, but then there's only so many enzymes, so no matter how many substrates there are, the enzymes can only work so fast.
reach the maximum speed of the enzyme, right? So this is our discussion about Charlie and the Chocolate Factory. So this is the situation where Charlie's dad is sitting there putting the toothpaste caps on the tubes, and the tubes are just coming too fast. And the other example would be I Love Lucy.
Like that episode.
She's at the chocolate factory. She cannot package the chocolate fast enough, so she's eating it, and she's like putting it into her shirts and pockets. She just can't keep up with it. All right. How about the next one?
As long as the substrate and the enzyme remain equal, no, nothing?
No. This is velocity and enzyme concentration, right?
I don't remember this.
So in the Charlie and the Chocolate Factory, his dad is the enzyme. So there's just one of him. And so he's trying to put the caps on as fast as possible. And then so that's this first chart over here. At some point, he's putting the caps on as fast as he possibly can. And it doesn't matter if more tubes come or not, it cannot go any faster than he's already going. Well, what was our next example of this? How do we talk? There was a bunch of Charlie's dads, right? So now instead of having one person at the end of the conveyor belt with the toothpaste caps, there are a whole bunch of Charlie's dads, clones of him. And so you can keep putting tubes as fast as you want if you keep increasing the number of enzymes. So as long as you have the more enzymes you put in, the faster the reaction is going to happen. So if you had 1,000 toothpaste tubes to put caps on and you had 1,000 Charlie's dads, how long would it take?
However long it takes one person.
Right, like 1 second to screw it on, right? So the more you have, the more enzymes you have, the faster it's going to go. More workers. So in that I Love Lucy, instead of just having one Lucy, there's like 90 of her. Okay.